Imagine the universe as a vast, dark stage. On this stage, countless celestial bodies perform an intricate ballet. Our solar system is one of these performing troupes. It is a family of planets, moons, asteroids, and comets. All of them are constantly moving, twirling, and spinning. This cosmic dance is driven by powerful, invisible forces. Understanding this motion is key to understanding our place in the cosmos. Our planet Earth is a dynamic world. It spins on its axis, giving us day and night. It also orbits our sun, giving us our seasons and our year. This realization was a profound shift in human understanding. We are not stationary observers, we are active participants in a grand cosmic journey. Every object in our solar system participates. The giant planets like Jupiter and Saturn have their own complex systems of moons. These moons orbit their planets just as the planets orbit the sun. Even smaller bodies like asteroids and comets follow their own paths. Prepare to be amazed by the sheer scale and beauty of our solar system's eternal dance through space and time. At the very heart of our solar system lies the sun. It is a star, a giant ball of hot glowing gas. The sun is enormous, containing more than 99.8% of all the mass in our solar system. This immense mass gives the sun its incredible gravitational pull. Think of gravity as an invisible tether. It reaches out from the sun and holds on to every planet, moon, asteroid, and comet. Without the sun's gravity, the planets would simply fly off into the cold, dark emptiness of interstellar space. The sun itself is not perfectly still. It also rotates or spins on its axis. Different parts of the sun spin at different speeds. The sun's equator spins faster than its poles. This differential rotation is fascinating. It contributes to the sun's complex magnetic activity like sunspots and solar flares, which can affect us here on Earth. The sun's formation itself was a process of rotation and collapse. Billions of years ago, our solar system began as a vast, swirling cloud of gas and dust. This cloud, called a solar nebula, slowly began to contract under its own gravity. The remaining material flattened into a disk, from which the planets formed. The planets of our solar system are like performers in a grand celestial show. They each follow a specific path around the sun. This path is called an orbit. These orbits are not perfect circles, they are slightly stretched out circles known as ellipses. The sun is not exactly at the center of these ellipses. It is at one of the two focal points of the ellipse. This means that a planet's distance from the sun changes slightly as it orbits. All the planets in our solar system orbit the sun in the same direction. If you could look down on the solar system from above the sun's north pole, you would see the planets moving counterclockwise. The planets also orbit mostly on the same plane. This plane is called the ecliptic plane. The speed at which a planet orbits the sun depends on its distance from the sun. Planets closer to the sun, like Mercury and Venus, travel much faster. Farther out, planets like Jupiter and Saturn move more slowly. This relationship between distance and orbital speed is another of Kepler's laws, governed by the sun's gravity. The dance of the solar system extends beyond just the planets orbiting the sun. Many planets have their own companions called moons or natural satellites. These moons perform their own smaller ballets orbiting their host planets. Our Earth has one large moon. It is a familiar sight in our night sky. The moon orbits Earth, just as Earth orbits the sun. This creates a system within a system, a smaller dance nested within the larger cosmic choreography. The moon's gravity also affects Earth, causing our ocean tides. Some planets are true moon collectors. Jupiter, the largest planet in our solar system, has dozens of moons. Its four largest moons, Io, Europa, Ganymede, and Callisto, are called the Galilean moons. Galileo Galilei discovered them with his early telescope. Saturn, famous for its beautiful rings, also boasts a large family of moons. Titan, Saturn's largest moon, is especially interesting. It is larger than the planet Mercury and has a thick atmosphere. Other moons are smaller, icy worlds. Each moon follows the gravitational pull of its parent planet. Section 5. Cosmic debris in motion, asteroids, comets, and their journeys. Our solar system is not just made up of the sun, planets, and their moons. There are countless smaller objects too. These are the asteroids, comets, and vast clouds of dust and ice. They are like the cosmic leftovers from the formation of the solar system. These smaller bodies also orbit the sun. They follow the same laws of gravity as the planets. However, their orbits can be much more varied and sometimes quite eccentric. Most asteroids are found in a region between Mars and Jupiter. This is called the asteroid belt. It is a vast, donut-shaped area filled with rocky bodies of all sizes. Some are tiny pebbles, while others are hundreds of kilometers across. Occasionally, their orbits can be disturbed. This can send them on paths that cross the orbits of planets, including Earth. Comets are different from asteroids. They are often described as dirty snowballs. They are made of ice, dust, and rocky material. Most comets come from the very distant, cold outer reaches of our solar system. Section 6. Our solar system's grand voyage journeying through the Milky Way. The dance of our solar system does not end with the orbits of planets and comets around the Sun. Our entire solar system, including the Sun and everything that orbits it, is on an even grander journey. It is moving through space as part of a much larger structure, the Milky Way galaxy. Imagine our solar system as a single car in a vast, swirling city of stars. This city, our galaxy, is immense. It contains hundreds of billions of stars, and our Sun is just one of them. Our solar system is located in one of the spiral arms of the Milky Way. This arm is called the Orion Arm, or sometimes the Orion Spur. We are about 2/3 of the way out from the galactic center. The entire solar system is orbiting the center of the Milky Way galaxy. It takes our solar system approximately 230 million years to complete just one trip around the galactic center. The speed of our solar system as it orbits the galactic center is astonishing. We are traveling at an average speed of about 828,000 kilometers per hour. Section 7. The Milky Way's majestic spin, our galactic neighborhood in motion. Just as our solar system orbits the center of the Milky Way galaxy itself is also in motion. It is not a static island of stars in an empty void. Our galaxy spins. All the stars, gas, and dust within it are part of this grand rotation. Imagine a colossal spinning pinwheel, and our solar system is just one tiny speck of light within it. The center of the galaxy, dense with stars and a supermassive black hole, acts as the gravitational hub. Stars in the Milky Way do not all rotate at the same speed. Stars closer to the center orbit faster, those further out slower, like planets around the Sun. However, observations show something surprising. Stars in the outer parts of the galaxy move faster than expected. This is key evidence for dark matter. Dark matter exerts gravity but does not emit light. Its presence explains these high rotational speeds. Our Milky Way is part of a group of galaxies called the Local Group. This group contains several dozen galaxies, including Andromeda. Section 8. Unveiling the movements. Evidence from observation and exploration. How do we know all of this? How can we be so sure about these complex motions, from planets orbiting the Sun to the solar system journeying through the Milky Way? The answer lies in centuries of careful observation, brilliant scientific deduction, and incredible technological advancements. It started with ancient astronomers patiently tracking the movements of stars and planets across the night sky. They noticed patterns, the regular wanderings of planets against the backdrop of seemingly fixed stars. The invention of the telescope revolutionized everything. Galileo's observations of Jupiter's moons, the phases of Venus, and the craters on our moon provided powerful evidence against an Earth-centered universe. Later astronomers like Kepler and Newton developed the mathematical laws that describe these motions. Newton's law of universal gravitation provided the fundamental explanation for why planets orbit stars and moons orbit planets. It gave us the tools to predict and understand celestial movements with remarkable accuracy. In more recent times, powerful ground-based telescopes and space-based observatories have given us even clearer views. We can now measure the precise positions and velocities of stars and galaxies. Radio telescopes allow us to map the structure of our Milky Way, even through obscuring dust clouds. Space missions have sent probes to visit other planets, moons, asteroids, and comets. These robotic explorers send back invaluable data and images. Section 9. Gravity's unseen hand, the conductor of the cosmic orchestra. Throughout this exploration of cosmic motion, one fundamental force has been the constant theme: gravity. Gravity is the unseen conductor of this grand celestial orchestra. It is the force that shapes the orbits of planets around the Sun. It keeps moons tethered to their planets. It holds stars together in galaxies, and galaxies together in clusters. Without gravity, the universe as we know it simply would not exist. There would be no stars, no planets, no galaxies, just a diffuse soup of particles. Gravity is what caused the initial cloud of gas and dust to collapse and form our Sun and the planets. Once formed, it is gravity that dictates their paths through space. Every object with mass exerts a gravitational pull on every other object. The more massive an object, the stronger its pull. The closer two objects are, the stronger the gravitational force between them. This elegant universal law, first formulated by Isaac Newton, governs the dance of the cosmos from the smallest moon to the largest galaxy cluster. Understanding gravity allows us to predict the movements of celestial bodies with incredible precision. We can calculate the trajectories of spacecraft on missions to distant planets.